What do these things have in common? The cross-entropy loss in your favorite classifier. The evidence lower bound, or ELBO, in a variational autoencoder. The PPO penalty term used in RLHF. The new GRPO objective from the DeepSeek-R1 paper. Or the variational bound for DDPMS that powers models like Sora. They all optimize the same 75-year-old number. In 1951, Solomon Kullback and Leibler published on Information and Sufficiency, introducing this quantity, the KL divergence. By the end of this video, you will see how this single equation underpins all 6 of these paradigms, right up to the latest world model and preference tuning losses. I'll assume you're familiar with transformers, the basics of reinforcement learning, and have at least heard of VAEs. Let's get started. The Kullback-Leibler divergence, or KL divergence, is a measure of how one probability distribution P diverges from a second reference probability distribution Q. For discrete distributions, it's defined as the sum over all outcomes, x of P of x, times the log of the ratio P of x over Q of x. The continuous form is analogous, replacing the sum with an integral. Visually, consider 2 Gaussian distributions, P and Q. The KL divergence integrates a pointwise quantity, shown on the second axis. Where Q underestimates P, the log ratio is positive, adding to the divergence. Where Q overestimates P, the log ratio is negative, and this term subtracts from the divergence. There are 3 core intuitions for the KL divergence. First, it's the expected value, under P, of the log ratio of the probabilities. This is the log of P of x minus the log of Q of x. Second, from information theory, it represents a coding penalty. Imagine you have symbols drawn from distribution P. The optimal code, like a Shannon code, would use log 1 over P of x bits for symbol x. If you mistakenly use a code optimized for Q, you'll use log 1 over Q of x bits. The KL divergence is the average number of extra bits you'll need per symbol. Third, from a geometric perspective, it is the Bregman divergence generated by the negative entropy functional. Crucially, KL divergence is not a true distance metric because it is asymmetric. The KL from P to Q is not equal to the KL from Q to P. This asymmetry has profound consequences in variational inference. When we minimize the forward KL, D of P given Q, we're trying to fit a simple model Q to a complex data distribution, P. This objective is mode covering. To avoid infinite divergence, Q must place probability mass everywhere P has mass, often resulting in a broad, diffuse approximation. Conversely, minimizing the reverse KL, D of Q given P, is mode seeking. It penalizes Q for placing mass where P has none. This forces Q to find and fit one of the modes of P tightly, ignoring others. The KL divergence is directly related to the cross-entropy, a standard loss function in machine learning. The cross-entropy H of P and Q decomposes into 2 terms, the entropy of P plus the KL divergence from P to Q. In a typical classification setup, the true data distribution P is fixed. For a single sample, P is just a one-hot vector representing the correct class. The entropy of this P is constant in fact, it's 0. Therefore, minimizing the cross-entropy loss with respect to our model's parameters, which define Q, is mathematically identical to minimizing the KL divergence. The loss we see during training is the KL term decreasing towards a constant floor defined by the data's entropy. To understand the KL divergence, we have to go back to its roots in information theory, specifically Claude Shannon's 1948 paper, A Mathematical Theory of Communication. Shannon asked, what is the minimum average number of bits needed to encode messages from a source distribution, P? The answer is the entropy of P, denoted H of P. It's the expectation of the negative log probability of each message. Now, what if we design an optimal code for a different distribution, Q, but use it to encode messages from P? The average code length we get is the cross-entropy, H of P, Q. The KL divergence is simply the difference between the two. It's the penalty, the extra bits per message we have to pay, on average, for using a code optimized for Q when the true distribution is P. This is also called the relative entropy. In machine learning, we're always minimizing some form of KL divergence, but the direction matters. When we perform maximum likelihood, we are minimizing the forward KL from the data distribution P to our model Q. This is DKL of P given Q. Because the expectation is over P, the model Q is encouraged to have high probability wherever P has probability, leading to mode-covering behavior. In contrast, variational inference minimizes the reverse KL from an approximate posterior Q to the true posterior P. This is DKL of Q given P. This direction is tractable because the expectation is over Q, a distribution we can sample from. As shown in the derivation of the evidence lower bound, or ELBO, this reverse KL term is what we're minimizing. This encourages Q to be 0 wherever P is 0, forcing it to choose one mode of a multimodal posterior, a behavior we call mode seeking. The KL divergence also has a beautiful geometric interpretation. Consider the space of all probability distributions over a finite set, which forms a shape called the probability simplex. On this space, the KL divergence is a specific type of distance-like function known as a Bregman divergence, generated by the negative entropy function. This structure leads to a generalized Pythagorean identity. If we take a distribution P and find its I-projection, R, onto some convex set of distributions, then for any other distribution Q in that set, the divergence from P to Q neatly decomposes. It's the sum of the divergence from P to its projection R plus the divergence from R to Q. This defines a sort of orthogonality. Taking the infinitesimal limit of this geometry gives us the Fisher information metric, which defines a local Riemannian metric on the manifold of parameters. Let's begin with the most common, yet often overlooked, application of KL divergence, standard supervised classification. When you train an ImageNet classifier, the loss function is cross-entropy. But what is cross-entropy? It's defined as the entropy of the true distribution P plus the KL divergence from P to your model's prediction Q. In classification, the true label is a one-hot vector. This is a deterministic probability distribution, and its entropy is exactly 0. This means the cross-entropy loss simplifies to precisely the KL divergence from the true one-hot label to the model's softmax output. So, every time you've trained a classifier with cross-entropy, you are implicitly minimizing KL divergence. An untrained model has logits near 0, so its predictions are diffuse. After training by minimizing KL, the model becomes confident, pushing the logit margin for the correct class far from the others. Next, let's look at variational autoencoders, or VAEs. The VAE objective function is the evidence lower bound, or ELBO. It contains two key terms. The first is a reconstruction term, which encourages the decoder to accurately reconstruct the input data X from a latent sample Z. This is standard for an autoencoder. The second term is a KL divergence that acts as a regularizer. It measures the divergence from the approximate posterior Q of Z given X to a fixed prior P of Z, which is typically a standard normal distribution. This KL term forces the encoder to produce latent codes that collectively resemble a simple, tractable distribution. This prevents the model from simply memorizing inputs and is what gives VAEs their generative capabilities. During training, we see both terms of this loss decrease as the model learns to both reconstruct well and organize its latent space. In their 2015 paper, Hinton and colleagues introduced knowledge distillation, a powerful model compression technique. The goal is to train a small student network to mimic a large, pre-trained teacher network. Instead of training the student on hard one-hot labels, we train it to match the teacher's full output probability distribution. The loss function is the KL divergence between the student's and teacher's softmax outputs. A crucial innovation is the use of a temperature parameter, T. Dividing the logits by T before the softmax makes the resulting distribution softer. This exposes the teacher's dark knowledge, the subtle relationships it has learned between classes. For example, a teacher might assign a tiny probability to truck for an image of a car. This is valuable information that the student can learn by minimizing the KL divergence, leading to better generalization than training on hard labels alone. Finally, we arrive at modern generative models like denoising diffusion probabilistic models, or DDPMS. The entire training objective for these models, the variational lower bound, or VLB, elegantly decomposes into a sum of KL divergence terms, one for each time step in the reverse diffusion process. At each step t, the model learns a distribution p theta of x sub t minus 1 given x sub t. This is trained to match the true, but intractable, posterior distribution q. The loss for that step is the KL divergence between these two. This connects diffusion models directly back to the VAE framework. Interestingly, not all time steps contribute equally to the loss. The KL terms are typically largest for mid-range time steps, where the model is doing the most meaningful denoising. This same VLB principle, scaled to spatiotemporal latence, underpins today's state-of-the-art video models like Sora. In reinforcement learning from human feedback, or RLHF, we train a language model using a reward signal learned from human preferences. A naive approach would be to simply maximize this expected reward. However, this invariably fails. The policy quickly learns to exploit the reward model, finding adversarial inputs that produce high reward but are often nonsensical or repetitive. The model's distribution collapses. The key innovation from the Instruct GPT paper, Aoyang et al. 2022, was to introduce a regularizer. We penalize the policy for straying too far from its original, pre-trained distribution, which we call the reference policy. The objective function becomes the expected reward minus a KL divergence term, scaled by a coefficient beta. This KL term acts as a leash, or an anchor, pulling the policy back towards the sensible distribution of the base model. Beta controls the strength of this leash. As the plot shows, there is a direct trade-off. Sweeping beta traces a Pareto frontier. A small beta allows for high reward, but the KL drift is large, risking incoherence. A large beta keeps the KL low and the model stable, but it puts a ceiling on the maximum achievable reward. The standard algorithm for optimizing this KL regularized objective is proximal policy optimization, or PPO, from Schulman 2017. PPO provides a second, implicit form of KL regularization. It's designed to prevent the policy from changing too dramatically in a single update step, effectively keeping the updates within a trust region. The mechanism is a clipped surrogate objective function. The key term is R sub t, the probability ratio between the new policy and the old policy for a given action. If an update would change this ratio too much, the objective function clips the potential gain. As the visualization shows, when the advantage is positive, there's a ceiling on the objective value, preventing the policy from becoming overconfident based on a single batch. When the advantage is negative, there's a floor, preventing an overly pessimistic update. This clipping is a simple, first-order method that approximates the more complex maths of a true KL trust region, like in the TRPO algorithm. Its simplicity and stability are why the combination of a KL penalty and a PPO optimizer has become the workhorse of RLHF. But what happens when this two-layer defense system fails? If the KL coefficient beta is too low, or if the reward model itself is flawed, the policy can engage in reward hacking. It discovers a degenerate strategy that maximizes the reward score but fails on the intended task. This can manifest in several ways. The model might hallucinate complex markdown formatting or code blocks because the reward model has spuriously correlated them with quality. It can become sycophantic, generating overly positive and agreeable text that panders to the user's expressed viewpoint, even if it's incorrect. Or it might suffer mode collapse, where it learns one high-reward response, like as a large language model, and uses it for a wide range of inputs. The training dynamics of such a failure are stark. The plot shows a classic reward hacking scenario. The reward metric climbs steadily, suggesting the training is successful. But beneath the surface, the KL divergence to the reference model after an initial stable period explodes upwards. At the same moment, any real metric of output quality, such as a coherence score or human evaluation, crashes. This divergence between the proxy, reward, and the true objective, coherence, is the telltale sign of a policy that has broken its KL leash. Let's now turn to two recent methods that refine the role of the KL penalty in policy optimization, starting with Group Relative Policy Optimization, or GRPO. Introduced by Xiao and colleagues in their 2024 DeepSeek-R1 paper, GRPO makes a surprisingly effective simplification to the PPO pipeline. The key insight is to drop the value network, or critic, entirely. Instead of learning a complex function to predict future rewards, GRPO computes a simple baseline from the immediate results of a batch. Specifically, it samples a group of G completions from the current policy and uses the mean reward of that group as the baseline. The advantage for any single completion is then its own reward minus the group mean normalized by the standard deviation. This works exceptionally well for tasks like mathematical reasoning, where rewards are often sparse and binary correct or incorrect. A learned value function struggles in this setting, whereas a group-based baseline provides a stable, low-variance signal to the policy gradient. Crucially, GRPO keeps the same KL divergence anchor to the reference policy as PPO, ensuring the model doesn't stray too far from its initial distribution. The full GRPO objective function should look very familiar. The policy update is driven by the clipped importance sampling ratio, rho sub I, times the group relative advantage, a sub I. This structure is identical to the PPO clip objective. Likewise, the regularization term is a direct penalty on the KL divergence between the current policy pi theta and the reference policy pi ref, scaled by beta. The only things missing are the value function and its corresponding loss term. By eliminating the critic, GRPO achieves significant memory savings. For a given model size, PPO must hold 3 models in memory: the policy, the reference, and the value network. GRPO only needs 2, the policy and the reference. As this chart shows, this can lead to a memory footprint reduction of around 33%. In the regime of training massive language models, where every gigabyte of RAM is precious, this is a substantial practical advantage. It allows practitioners to train larger, more capable policy models on the same hardware, trading a learned baseline for a cheaper, statistically grounded one. While GRPO simplifies PPO, direct preference optimization, or DPO, sidesteps it entirely. Proposed by Rafalov and colleagues in 2023, DPO is a powerful reformulation of the RLHF problem. It starts with the same objective maximize reward while staying close to a reference policy via a KL's constraint, but solves it in closed form. Assuming a Bradley-Terry model for human preferences, the optimal policy can be derived directly, collapsing the entire reinforcement learning loop into a simple binary classification loss. The DPO loss is the negative log likelihood of a sigmoid function. Its argument is beta times the difference in the log probability ratios of the winning and losing completions. In essence, training with DPO directly increases the log likelihood of the preferred response, y sub w, relative to the reference, while decreasing it for the rejected response, y sub l. This means no reward model, no online rollouts, and no complex PPO machinery. We simply train the model on a static dataset of chosen, rejected pairs, just like supervised fine-tuning. This plot shows the effect. Before DPO, the preference margins are centered around 0. After DPO, the distribution has shifted significantly positive, indicating the model has successfully learned the preference mapping. Let's move to our final frontier, world models. These models learn a simulator of the world directly from data. A prime example is the Dreamer v3 agent from Hafner and colleagues in 2023. Its core is a recurrent state space model, or RSSM. The RSSM maintains a deterministic recurrent state, H sub t, summarizing history. From this, it predicts the next stochastic latent state, z sub t, forming a prior distribution, p of z sub t given h sub t. This is the model's imagination. When the next real observation, x sub t, arrives, the model uses it to correct its belief, forming a posterior, q of z sub t given h sub t and x sub t. The dynamics loss is the KL divergence from the stop gradient posterior to the prior. This forces the model's predictions to be consistent with what actually happens. The KL divergence, once again, anchors a model's imagination to observed reality. This principle extends directly to the 2024 wave of generative video models, like the Sora class systems. These are effectively world models trained on vast internet video. At their heart, they are diffusion models operating on spatio-temporal latents. The training objective for a denoising diffusion probabilistic model, the DDPM, is a variational lower bound, or VLB. This VLB is composed of a sum of KL divergences, one for each step in the denoising process. For video generation, this means every frame-to-frame transition, every subtle motion, is being optimized by minimizing a KL divergence. The same equation that underpinned early VAEs is now training models that simulate complex physical dynamics. From a simple prior over images to a complex prior over world trajectories, the KL divergence has scaled with our ambitions, becoming the engine of modern generative AI. So, why does this one mathematical object keep showing up, from statistical testing to world simulation? There are at least 4 deep reasons. First, as motivated by Kullback and Leibler in 1951, it is the expectation of the log likelihood ratio, the canonical and sufficient statistic for hypothesis testing between 2 distributions. Second, in its infinitesimal form, the KL divergence defines the Fisher information metric, which equips the space of probability distributions with a Riemannian geometry. Third, it is a Bregman divergence generated by the negative entropy function. This gives the probability simplex a flat geometry, making optimization tractable. And fourth, the principle of minimizing KL divergence is dual to the principle of maximum entropy, a cornerstone of statistical mechanics and information theory. It's not just a loss function, it's a fundamental concept connecting information, geometry, and learning. Let's recap the KL divergence's journey. Classifier cross-entropy is a KL divergence. VAEs use reverse KL to regularize the latent space. Hinton's knowledge distillation transfers knowledge via KL on soft targets. The DDPM variational lower bound is a sum of KLS, one for each reverse step. In RLPPO's KL penalty acts as a Trostrigian leash. GRPO extends this leash to multiple preference sources with a group relative KL. Rafalov's DPO finds a closed-form RLHF solution by linking KL to preference data. Dreamer v3 uses it for dynamics prediction, Sora for spatio-temporal diffusion. 75 years on, this one number is still the shortest distance between probabilities and the longest lever in AI. Subscribe for more. Links to Wikipedia and the key DeepSeek, DPO, and Dreamer v3 papers are in the description.